which is 9 by 1. And let's assume that we are going to have this transformation. This one. What is row 3? We exchange it with row 4. Okay? How can we represent this linear operator using elementary matrices? Let's see. This is 1, 0, 0, 0, 1, 0, 0, 0, 1. This is the identity matrix, okay? And sorry, this is 3 by 3. Let's assume we do row 3 with row 2, okay? So if we do this operation on this identity matrix, what do we get? We get 1, 0, 0. Row 2 with row 3, this becomes 0, 0, 1, 0, 1, 0. Okay? So if we have a vector where we just want to change 2 rows, we multiply that vector with this matrix. Does it make any sense?
Yes.
Yes.
Okay, then I can ask help from you. Can you do the following? You multiply on your programming units, calculator or computer. Multiply a number which is 123,456,789. Multiply this by 2, by 3, by 4, up to 23. And can you write your answers here in the comment section? So you just write here the first number times 2, you write the answer, then times 3. Can you start writing it?
What should we do? I didn't get it.
Do this. 53 milion. E 456.000, e 789. Shumëzim për 2, sa bëjmë? Shkruajini te komentet, te klasat, ta shikojnë gjithë. Shumëzojnë me kështu, me makinë llogaritse. Okay. So Ray did the first one. So I have a question for multiply. Now you did it with 2. You are so many in this class. So could you please multiply by 3, 4, 5, up to 23? Everyone picks a number and write it down over there. So my question is to Kevin. So Kevin, the result. What do you observe in the result that you just reported? Do you have any one of the numbers that is mentioned twice?
No, there isn't.
No. So what you have as a result, you just have a new combination or a permutation between the numbers that are provided, okay? So this is what you observe, which means that if you want to multiply these numbers, how can you do that using matrices? Or let me ask, for example, Arvi. Arvi, what do you observe in your multiplication by 23? Do you have any number that repeats itself twice? At least twice?
No.
No. But apparently you have a 0, which is much more than you have here, which means that this number or this vector, you could include a 0 for larger numbers. This would be 10 by 1, okay? But then my question is, how can you represent? So let's look at the number by Arvi. He's saying that we can multiply this number, and this is equal to, let's see what was the answer. This is equal to, I see if I can read it. Arvi, where is your answer? I lost it. Arvi, okay, it's 2.
I'm sending it again.
No, okay. 2839. Arvi, 2839, 569, 2339, 567.
127.
Okay, now as an exercise, what do we have here? We have a vector 10 by 1, which we can multiply with another matrix, which is 10 by 10, and then we get this result, right? My question would be the following. Find with which matrix, 10 by 10, can we multiply this initial vector to get this? How would you solve this problem? Now, if we have a look here, it looks like row 3, it hasn't changed at all. Row 5, it has not changed at all. We observe, so we observe that 1, 2, 8 is a triplet, 1, 2, 8. So what we can do here is that we can get an identity matrix which is 10 by 10, and then we just change the first row with the second. Okay. Then what it does is that the first output, this would be 2, 1. Okay. Then we may need to change the place of 8 and 1. Okay, this becomes 2, 8, 1. But how can we do it? We can do in a similar way like here. Okay, and as a good exercise for you, I can even open an assignment on Google Classroom. You can work on this one. You pick a number and try to, and your answer would be the following. Given an initial vector, you get the multiplication, but express how you get this multiplication by multiplying it with a matrix. Okay. So if we want to do the first 3 operations, how? Let's say if we want to interchange the second row with the first row, the first row would be this 0, 1, 0, 0, 0. This one would be 1, 0, 0, 0, and this is a 10 by 10 matrix. Okay. So if we multiply this with this, what will happen is that we'll just interchange immediately 1 and 2. This is it, right? And then we may want, sorry, 1 and 2, this will be 2, 1, right? Okay, 2, 1. No. Okay, sorry again. This is 1, 2, this is 2, 1. Then we want to interchange the number 1 and 8. So how do you do 1 and 8? You just generate another matrix where you have here 0, 0, 0, 0, 1, and you put the 1 here, 1, 0, 0, 0, 0, and so on. Okay, so this is the 8th row. This is the first row. Okay, so it could be a good exercise for you. So you might expect a homework featuring this specific example on the Google Classroom. Now, I also added this explanation because you asked me some more details of how do we do this. In order to figure out all these possible permutations, you can even write a program about this one. So how can you obtain from this to this? You may do continuously interchange numbers, and if the numbers is too large, you could even try to optimize this problem in order to take as less steps as possible. But let's leave this one for you to think when you do the homework. Let's move forward with a different approach or different aspects. So we did the elementary matrices, and then we can say that, for example, if we have a matrix A, and we modify this matrix A by multiplying with an elementary matrix, and we get the matrix B. If this is an elementary matrix, the E, then we call A and B that they are row equivalent. So this would be row equivalent if A and B can be found using a finite number of elementary matrix multiplication. So this is the concept of row equivalence. And now we're going to report a theorem. And in this theorem, we are going to observe 4 different statements which observe an equivalence. And so for any matrix A, which is a square matrix, n by n, the following statements are equivalent. These statements are the following. A inverse exists. This is the first statement. Now, when we say that the following statements are equivalent, we mean that if the first one is true, then the second one is then also true. So AX is equal to B, hence a unique solution for B element of Rn. Okay? So apparently, if the inverse of A exists, then any equation that can be written Ax is equal to B is consistent. What was a consistent system of linear equations? It was a system which had a solution. Now, this system, it has a solution, but it looks like a good one because it has a unique solution, which means only one solution point. We don't have the solution represented by a line, or we don't have the solution represented by a union of a whole plane. Okay, so we have just one clear point. The other equivalent statement is the following: Ax equal to 0 has only the trivial solution. So, what is a trivial solution? The trivial solution, so Ax is equal to 0, this equation also can have an infinite number of solutions, okay? Or maybe only one. But whichever way it could be, the moment that A has an inverse, we say that this equation has only one solution, which is the trivial one, and the trivial solution is this. Because we know that for any 3 times x is equal to 0, what is the trivial solution here?
X equal to 0.
X is equal to 0. Okay. So this is the third statement. The fourth statement is the following. The reduced row echelon form of matrix A is equal to the identity matrix. Okay. So these statements are equivalent, which means that if you have a matrix A and you are trying to determine the reduced row echelon form, and if in the end you make the leading elements all ones, and you see that you are left with the rest are all zeros, that means that this is an identity matrix. Then you think for a moment and say, okay, if I can get this A into being transformed into an I, then the inverse exists, right? And the inverse, as we saw before in the previous session, it looks like the inverse is going to be equal to the multiplication of all the elementary row operations. Now, this is an important theorem. And we could go over another example, but before doing that, once we're done with this, we define a new quantity. And this new quantity that we are going to define is called the determinant. It's a Dalori, that we call it in Albanian. So here we have the determinant. Now, determinant is very strange. I mean, the different properties that the matrices have, or the matrix parameters have, it's hard not to be impressed, because as we're going to see later on, the value of the determinant of a matrix, it is very strongly related also with other important parameters, such as the eigenvalues, but we have not covered these materials yet. We're going to do them very soon. But let's see the definition of a determinant. Now, determinant, it's good to start with a definition of the smallest possible matrix, which is a 2 by 2 matrix. So for any matrix which is A, B, C, D, first of all, determinant, we denote it in this form. This is equal to the A. So if we see any absolute value elements or symbols across a letter, that would be the determinant. In this case, determinant of this matrix, let's write determinants like this, we don't have these. This would be AD minus BC. So this is the determinant of a 2 by 2 matrix. Determinant, you can also perceive it as being the volume in the multi-dimensional space. So if we have, actually it's good to check this one, but for 3D, if you have a 3 by 3 matrix, you can assume that you have 3 vectors. So here you have a parallelogram, and here you get another one, here you get another one. And the determinant of the three elementary matrix, it is numerically equal to the volume of this cuboid. Okay, so determinant is really an interesting factor, and if this is the volume, we should know. So if you have any matrix A, which would be, let's say, 3 by 3, the determinant of this A would be equal to lambda 1, lambda 2, lambda 3, which this is somewhat equivalent to having a cube and finding the volume of this cube. But you can take a note of this one, and when we go into the future weeks, when you do the eigenvalues, you might remember this again. And the determinant, let's assume we have a larger matrix, such as 1, 3, 5, 2, 0, 1, minus 2, 3, 1. The determinant of the 3 by 3 matrix, in order to define that one, what we do, we expand, let's call it this way. We expand along row 1, okay? When we say that we expand along row 1, we mean that, let's see what the row 1 is, 1, 3, 5. And this one, let's do this step by step, this would be equal to 1 times the determinant of small matrix. And if we pick up this one, then we exclude the first row and the first column, and we get, so if we remove the first row and the first column, what is left? We get this, right? Then
We get 0, 1, 3, 1. Oh, yes, sorry.
okay, thanks. But there is also a useful tool that we use when we use the matrices, which is this factor. We have this factor which is minus 1 to the power I plus j. Okay, so we are going to see this one very often when we deal with matrices. So I and j, they are the indices of each one of the entries. So let's assume this is A, and let's see the following. What is A11? A11, this would be minus 1 to the power 1 plus 1, okay, which would be equal to plus 1. So here we put a plus 1. Let's look at this A23, which is second row, but we are somewhere here. What is A23? This corresponds to minus 1 to the power 2 plus 3. What is this?
Minus 1.
This is 1, so this is minus. What about A13? This is minus 1 to the power 1 plus 3. This is equal to plus 1, right? So this is plus, minus, minus, plus, minus, sorry, plus, minus, plus. So we can construct like an array of signs, negative and positive signs, which greatly depend on where in the matrix we are. Okay? So we always start with plus here, then we go plus, minus, plus, minus, plus, minus, plus. You go backwards, minus, plus. Whichever way you go to the next element, you get these minus pluses. So why do we mention this? We mention this because when you do the expansion along the first row, we have here the following: plus, minus 1 to the power. What is the index of 3? What is A12? First row, second column? It's 3, right? So A12 is 3. So here, 3, it has a minus. So this is plus minus 1 times 3 times 2, 1 minus 2, 1. 2, 1 minus 2, 1. Plus minus 1. Sorry, let's do this one. 1 plus 2. Okay? And here we have 1. This 5, this is 1 plus 3 times 2, 0 minus 2, 3. 2, 0 minus 2, 3. Okay? So if you want, we forgot to multiply by 5 here. So if you want, you may remove this minus 1s completely, because you know that it's going to be plus minus interchangeably. Okay. So again, the determinant here is going to be the following: 1 times what is the determinant of this little matrix?
-3.
-3. Then what is this?
-3.
-3 times
4
4.
yes, 4 is true. And then
plus 5 times 6.
Oh, 6, right?
Yes.
So here we have -3, -12. This is -15 plus this is 15. Okay, so this is the determinant of this matrix, of this 3 by 3 matrix. Now that we know the determinant, we can try to define what is the inverse of A. And to find, wait a second, okay, so sorry, I erased this one completely, but which is fine, but I can write this for demonstrative reason. This is 1, 3, 5, 0, 1, 3, 1, and then 5, this is 2
Minus 2.
Okay, I can read it from here, okay. So, now to find the determinant, we expanded along row 1, okay, that's good. We can find the determinant also if we expand along, you pick a column, any other column or row. Which one would you like to expand over?
Row 3.
Row 3, we can even do...
Row 2 or column 2 is perfect because there's a 0 in it.
You are right, okay. So we can even pick, shall we pick second column? Let's expand, okay, so let's do this one. Let's expand along column 2. You are right, it's good to take out column 2 because we have a 0, so it will make the calculations easier. So if you are in an exam or in a stressful situation, picking the columns or the rows that are full of zeros could be a good choice. But let me say also this one. Okay, maybe I'll come this one a little later, but let's do this expansion. What do we get here? First, this is plus minus. So here we have -3, okay, times the determinant of 2, 1 minus 2, 1, 2, 1 minus 2, 1, plus minus plus 0 times something, okay. This is plus minus 3 times, so we're talking about this 3. It's going to be 1, 5, 2, 1. 1, 5, 2, 1. So this will be equal to, so what is the determinant here?
0. 0 times 3.
This is 4.
Yeah. 4, yeah.
Minus 3 times 1 minus 10 minus 9. So here we get 27 minus 12, 15. Okay, so still we got 15. Okay, why is this 15? Because this is like the volume which is constructed by 3 vectors, and these vectors are like this. The first vector is 1, 2, minus 2. Where is 1, 2, minus 2? X, Y, Z. 1, 2, minus 2, X is 1, Y is 2, Z is minus 2, become 2 units down here. So this goes like this, become 2 units down. This is the first vector, okay? The second vector, 3, 0, 3, 1, 2, 3, 1, 2, 3. The Y is 0, so this goes like this. This is the other vector, okay? So in space, they are going to define a region which has some volume, which you can fill it with water. The third vector is 5, 1, 1. This is 1, 2, 3, 4, 5. Then you come 1 unit this way, and this here, you come 1 unit up. So there is another vector which is going to be somewhere in here. This is here. Anyway, I'm not the best drawer, but you can also come like this comes like this. So there is like a cuboid which extends down here, and the volume of this one is 15 units cube. Okay, so for any matrix A, which is n by n, because if we want to find the inverse, this is what we are going to cover next. We can find the inverse of a matrix only if it is a square matrix. Cleo, you have any comment?
Well, we're very tired.
You're very tired? Yes. Then we'll move very fast. So for any matrix A, we can define a matrix Mij, which is called the minor matrix. Okay, the minor. And for any minor matrix, we can define then a cofactor Cij, which is minus 1 to the power I plus j times Mij. So this is the cofactor. And then from the cofactor, we can define an adjoint of A, which is equal to cofactor matrix transpose. And from here, we can define the A inverse. This is equal to 1 over the determinant of A times the adjoint of A. Okay? So the only thing which we don't know enough so far, so this is the steps, these are the steps which you need to conduct to find the inverse of a matrix. And the only thing that we need to know is the definition of a minor. The definition of a minor, it is the determinant of the matrix after we remove ith row and jth column. Okay, so let's assume we have a matrix here which is 1, minus 2, 3. Actually, not all the matrices have a defined determinant, so let's pick a number 1, 2, 3, 4, 1, 1, minus 1, 3, 0. So let's assume we have this matrix. So this is A, okay? We are here. To find the inverse, we need to determine the minor. What is a minor? Minor is a matrix which is going to be equal to. So what is M11? M11, it is the determinant of a matrix after we remove the first row and the first column. So if we remove the first row and the first column, what do we get? We get this, which means that what is M11? It's minus 3, right? What is M22? M22, we remove the second row and the second column. And can you help me what we are going to get? What is the M22?
Minus 3.
That's probably 3. Would you agree?
Yes.
Okay. Then let's find M12. What is M12? M12, first row, second column. We are talking about this number. So we are left with what? 4, 1, minus 1, 0. What is M12?
1.
1. So this is 1. What is M13? So if it M22, we found it was 3. Then this number, it is, we exclude the first column and the second row, we get minus 9. This is correct, probably minus 9. Then here we get 12 plus 1, this is 13. This number, for here, we remove the third column and the second row, we get 1, 2 minus 1, 3, that's 3 plus 2, 5. Okay. Here we get 2 minus 3 minus 1, 1 minus 12 minus 11. Then here we get 1 minus 8 minus 7. Okay. This was the minor. So we just did the multiplication of pairs of numbers and we found a minor. Then what is the cofactor? So these calculations we got them. The cofactor is the multiplication of the minor with these numbers. So because this is what this factor is doing.
I didn't understand how you got these numbers in the matrix.
Like let's recalculate them. We can recalculate them. Okay. So let's say we want to find what number we should put here, okay? What is the address of this number? This is M23, right? M, third row, second column. This is equal to, we have a look at the original matrix A, and we have to remove the third row and the second column, right? Pra 3 është rreshti i tretë, kolona 2. Po të heqim këtë, edhe këtë, ç'a ngelet? We get ngelet nish treshi, 4 nishi, dakor? Dhe pastaj, determinanti i matricës 2 me 2 është i barabartë 1 herë 1 minus 4 herë 3.
Aha, e kështu vazhdon për gjitha, domethënë.
Po, ç'ndro.
Okay.
Okay, so we go like this, and then from the minor matrix, we multiply all of these numbers with these factors, okay? So then we get the cofactor, which is going to be equal to, we get here minus 3, so let me take this out for a moment. This is minus 3, minus 1, 13. Here we change the sign. This will make this 9, 3, minus 5. Here we don't change the sign. Here we change the sign. We make this 11. And here, if we multiply minus 7 with plus, we get minus 7. Okay. So this is the cofactor. Then we find the adjoint of A. What is the adjoint of A? This is the transpose of this matrix. The transpose is defined as, we look at the first row, okay, and we make it a column. This becomes minus 3, minus 1, 13, and here we have 9, 3, minus 5, and here we get minus 1, 11, minus 7. Okay? So now that we found the adjoint, what is left? What is left is that we have to divide this adjoint with the determinant. What is the determinant of this matrix A here? So what is the determinant? Let's expand this along the third column. So let's expand along the third column to find the determinant. So in this case, we get what? Plus minus plus. This is 3 times 4, 1 minus 1, 3. 4, 1 minus 1, 3. Plus minus plus minus. Minus minus 1 times 1, 2 minus 1, 3. 1, 2. Minus 1, 3. And this would be equal to 4 times 3, 12, plus 1, 13, times 3, 39. Here we have 3, plus 2, 5, minus 5, this is 34. Okay, the determinant is 34. So here, we divide by 34, and then here, we just multiply with minus 3, 9, minus 1, minus 1, 3, 1, 13, minus 5, minus 7. So I just multiply divided by 34, the adjoint of A. So today, we just saw how to calculate the inverse of a specific matrix using two different techniques. One of them was using the elementary row operation. So we merge the matrix A with the identity matrix, and we do the same operations on A until we get the I, the identity matrix, and the next one next to it will be the A inverse. I have a comment here. The rule of Saros. There is a question. I don't know what is the rule of Saros, really. Can the rule of Saros be used since it gives the same determinant value? Probably it does. Is this a rule that you multiply? You add two columns here and you use these straight lines, right? Right, but I think you can use it. Yeah, I mean, it's the same, it's a technique, it's a tool, which is useful, yes. I think you add two columns here and you draw 3 diagonal lines, you subtract the other 3, yes, you can use it. I did not know that that one is called Saros Rule. Yes, Ariane has a comment, and Erando, you can explain to Cleo and Ariane later what is this Saros Rule, okay? But here we observe the second method, how to obtain the inverse of matrix A. Do you have any question?
No.
No. Okay. If there is no question, then I think we can give an end to this session, for today, and for anything